So we're going to be talking about the Curtius and the Beckmann. The Curtius is basically developing an isocyanate from an acid chloride, and we're going to basically start with acid chloride or acyl chloride. And the key property of an acid chloride that we need to think about is that this is it's a good leaving group. So that means that it is really reactive, and this carbon right here has an extreme partial positive charge because it's got two electronegative atoms right next to it. All right, so we're going to be using azide with this. And basically, the first step is, as usual, we're going to have a nucleophilic attack. As I just said, chlorine's a good leaving group, so we're going to kick it out. Now I'm going to just quickly draw some resonance structures, basically so that we can get the motivation to create this isocyanate. Let's draw an arc here. So for context, our isocyanate, something of this form. So I'm going to resonate this down and this here, because once again, similar to what we did in the Schmidt, we're trying to get that N2 leaving group. As you can see, we are already close to the N2 leaving group right here. I'm just going to highlight it. We just need to find a way to break this bond and send on to that nitrogen. And what we're going to do is we're going to resonate this down. Just another resonance structure. Alrighty. Now to get this to leave, we need to basically catalyze this somehow, and we're just going to send this right back down. But this bond right here is going to break, connect to the nitrogen. Now this has three things in it, three bonds to it, so this bond can break, and we'll lose the N2, which is perfect for us. This is what's driving the reaction again, and we form a double bond to that carbon-oxygen. So we have oxygen double bond to a carbon. That carbon is double bonded to a nitrogen. And this R group has moved over to the nitrogen, so we get, and that's our product, it's an isocyanate. I'll put that down too. So what's important for this is to note that isocyanates are, the carbon is pretty electrophilic again. As you can see, based on partial charges, these are partially negative, and this carbon correspondingly has partial positive charge, which means that if we took something like a hydroxide, easily attack it, and we could create a compound with this, and then we could basically push this all into, I think, a carboxylic acid looking thing. No, we will decarboxylate this. So we're going to, I think, protonate. We'll protonate this. No, we won't. We'll protonate this, but we for sure resonance structure. Now we're going to protonate this with water. Okay, now we basically get like a, say like basically a proton transfer. You're going to deprotonate this one, right? We're going to deprotonate with our base. And not manage space well. Although this is not a good leaving group, we're going to actually kick it out because we form as a side product CO2. And this is another thermodynamic sink. So I will push it forward, and then we're going to have which we take from our conjugate acid of water and we protonate it. And now we generate CO2 and H2N R. And that is why isocyanics are important, is because they are good electrophiles, and you can attack it with a nucleophile and decarboxyl it. As you can see, you're a CO2 leaving group. All right, now for the Beckmann. So previously I mentioned that with a carbonyl you can attack it with basically some kind of nitrogen amine compound, and in this case we attacked it with a nitrogen connected to a hydroxyl. And why this is important is in the Beckmann you can use that hydroxyl as a leaving group. So we will start with our carbonyl. What do we use? What did we use previously? Do I have it written down? I do. Cool. Generic carbonyl. And we use that and acid to generate our hydrazone. And now we will go under acidic conditions. The first thing we're going to do is we're going to, let me just do this. We're going to protonate this oxygen. We're basically making this a leaving group. Now we have a good leaving group, the water, and we're going to kick it off, which is kind of crazy. But this sigma positive break, connect to the nitrogen, kick this water off. It doesn't seem particularly favorable, it doesn't seem intuitive, but it is what happens. And we're going to get one, two, three, four, 5, 6, 7. 7-member ring. This carbon had 4 bonds on it, now it has 3, so he's got a positive charge, and we have a random water molecule sitting around. Water attacks that positively charged carbon. But before we jump to that, I want to note there is a resonance form here. It's really unstable because you generate like some really weird straight chain. So it's a thing, but no, this is positively charged basically. There's also a positive character. We'll attack it with water, which is lost. And we generate 2, 3, 4, 5, 6. That. And now we're going to deprotonate our water. Almost there. We need to now transfer the proton over to the nitrogen. And so we'll just go here. Nitrogen compounds are pretty good bases in general. So whenever you see nitrogen and hydrogen sitting around, you can almost bet that you're going to protonate the nitrogen. All right, positively charged nitrogen. So the CO double bond is stronger than the CN double bond. So we're going to create that CO double bond, which is more stable. Although it puts a positive charge on the oxygen, which isn't too happy to happen, but it is what happens. I'm just reorienting the structure right now. One, 2, 3, 4, 5, 6, 7. 7-member ring now. And then we just get last equivalent of water. Deprotonate. And that generates our product. This is kind of similar in idea to the Schmidt. We are adding in a nitrogen into a ring. This is a ring expansion in some sense. With the Schmidt though, you're getting a single nitrogen added in. In the Beckmann, we get an NH added. But yeah, that's the main difference. And you also get like a different rearrangement going on. Our rearrangement in the Beckmann is a lot earlier than in the Schmidt.